Let's tackle question 1, a classic NCERT lift problem. A man of mass 70 kg stands in a lift accelerating upwards at 5 meters per second squared. What is the weighing scale reading? The standard textbook trap requires drawing a free body diagram, setting up the equation n minus mg equals ma and carefully balancing the vectors. Under exam pressure, flipping a single sign will ruin your answer and waste 2 minutes. Here is the 30-second shortcut, the effective gravity hack. When a lift accelerates upwards, the floor pushes into you, making you feel heavier. We simply replace standard gravity G with effective gravity, which is G plus A for upward acceleration. Let's calculate the reading. Weight equals mass times effective gravity. That is mass times G plus A. Plug in the values 70 times 10 plus 5. 70 times 15 gives us exactly 1050 newtons. Option B is your correct answer. Add the acceleration for upward motion, multiply by mass and lock in your marks. Moving on to question 2. A classic wall reflection trap. A billiard ball of mass m strikes a rigid wall at an angle theta with the normal and rebounds with the same speed v. What is the magnitude of the impulse? Let's draw it out. Here is our vertical wall, the horizontal normal line, and our ball hitting at angle theta and bouncing off. The speed v remains constant. The standard textbook trap, breaking velocities into x and y components, setting up vector subtraction and messing up the negative signs. It's an easy way to lose marks. Here is your 30-second wall reflection hack. Simply look at the component perpendicular to the wall. The parallel component v sine theta doesn't change, but the perpendicular component v cosine theta exactly reverses. Since impulse is change in momentum, it is simply double the perpendicular momentum. That gives us 2mv cosine theta. Option B is our answer. Remember, impulse is always double the perpendicular component. Lock it in. Question 3 is a high-frequency NEET favorite. A machine gun fires n bullets per second, each of mass m with velocity v. What force is required to hold it steady? Let's picture it. The gun recoils backwards as it continuously fires a stream of bullets forward at velocity v. The standard trap? Students try to calculate the momentum for a single bullet, set up an impulse equation and get completely stuck trying to find the time variable. Here is the 30-second NMV hack. Since force is the rate of change of momentum and n is already defined as bullets per second, the holding force is instantly equal to n times m times v. No complex calculus or time conversions needed. Option C is the correct answer. Just multiply the three variables together and save your time. Moving to question 4, a classic equilibrium puzzle. A 6 kg mass is suspended by a rope and a 50 Newton horizontal force pulls the midpoint. We need to find the angle it makes with the vertical. Let's visualize the setup. The ceiling, the angled rope, the midpoint P, the 60 Newton downward weight and the 50 Newton horizontal force pulling to the right. The standard textbook trap, resolving tensions into sine and cosine components, dividing two simultaneous equations and hoping you don't make an algebra mistake. What a waste of time! Here is your 30-second vector triangle hack. Because the point is in perfect equilibrium, these three forces must form a closed right-angled triangle. We simply map the horizontal force over the vertical weight. Tan theta is just 50 over 60. That instantly simplifies to 5 over 6. So theta is tan inverse of 5 over 6. Option E is our correct answer. Build the triangle, divide the forces and secure your marks. Question 5 brings us to connected blocks. Two blocks of 10 and 20 kilograms are pulled by a 600 Newton force applied to the 20 kilogram block. What is the tension in the connecting string? Let's sketch the train. We have a horizontal surface, the 10 kilogram block in the back connected by a string to the 20 kilogram block in the front, which is being pulled by 600 newtons to the right. The standard textbook trap, first calculating the entire system's acceleration, then drawing a separate free body diagram for the smaller block to finally find the tension. It's a two-step trap that eats your clock. Here is your 30-second pulling ratio hack. Tension is simply the total pulling force multiplied by the mass behind the string divided by the total mass. Let's plug it in. Tension equals 600 times the mass being dragged, which is 10, over the total mass of 30. That's 600 times 1/3, which instantly simplifies to 200 newtons. Option B is our correct answer. Just grab the mass behind the string, multiply by total force, divide by total mass and move on.
Our final question for part 1 covers the classic Atwood machine. Two masses, 12 kg and 8 kg, are hung over a frictionless pulley. Find the acceleration. Let's draw the pulley system. We have the fixed ceiling, the circular pulley, the lighter 8 kg mass accelerating up, and the heavier 12 kg mass accelerating down. The textbook trap, writing two separate force equations for each block, balancing tensions and solving them simultaneously. This algebraic nightmare drains your exam time. Here is your 30-second net pull hack. Acceleration is simply gravity multiplied by the difference in masses divided by the total mass. Let's plug the numbers. 10 times 12 minus 8 over 12 plus 8. That is 10 times 4 over 20, which perfectly simplifies to 2 meters per second squared. Option B is our final correct answer. Heavy minus light over total mass is all you need for pulleys. That wraps up part 1. Like and subscribe for part 2.
If you found this visual breakdown helpful, you need to put that knowledge to the test right now. Head over to neetapp.in or download the NEET app today. We have chapter-wise, concept-wise and level-wise MCQs from easy to moderate to hard waiting for you to master. Plus, you can take free full syllabus mock tests, grab premium NCERT-aligned study materials and enroll in our ultimate NEET crash course to supercharge your prep. Don't just watch physics, conquer it. Hit that subscribe button, click the link in the description and I'll see you in the next video.